illustrating to you a cellular automata machine simulator that's based on this great book by Tommaso Toffoli and Norman Margolus from MIT Press, Cellular Automata Machines. So this really, they made hardware for the IBM PC that executed a wide range of cellular automata at 60 frames a second, and they were able to perform all these incredible experiments, and they documented them in the book. And it uses Forth as a programming language for defining the rules. So this is a really amazing book that I ran across the actual hardware and got the book and kind of reverse engineered it. But they have Forth code in this book to define different rules. And I was using a Forth system and made a compatible programming language for that. So here's like a Forth program, diamonds. And you can see it's visually north, west, center, east, south. Forth is almost a visual programming language here, or to plain zero. That's the whole definition of the rule. And the rules run over all possible combinations of inputs, and it makes a lookup table. And then the hardware loads the lookup table. This is the Forth software that they used to program the IBM PC. Isn't it beautiful? I just love their right-handed indentation style. Nobody does this but these guys. So it's like really ends all arguments about indenting. But anyway, this controls the hardware, which Forth is really great at doing. And you can have assembly language. And so I have this nice Forth system on the Sun that can link in C libraries and control them, call them directly. And so I wrote an emulator for the hardware in C, and then I linked it into Forth and made Forth maps for all the data structures. And then, kind of a wrapper around. So I had this Forth, like their Forth, that was running a simulator instead of hardware. And then I can define the same rules. And the rules this is the actual rule compiler. So basically, the hardware has these address lines, and the rules map. Neighborhoods have different sets of address lines. The Moore neighborhood has all that 8 neighbors plus center. Von Neumann only has 4. Margolus neighborhood is very interesting. It's a rotationally symmetrical neighborhood that you define in terms of me, my opposite. See, there's center and opposite and clockwise and counterclockwise. This is great for doing billiard ball simulations and and then there's Margolus with the additional phase of time, even odd step, or horizontal and vertical phase, which are different ways you can make sort of multiplex things. So anyway, this corresponds to the hardware, and then they have all these macros like, what are my 2 bits of wests? And then now this is really just a emulator for that. It's rewritten. And anyway, let me get to the fun stuff. So these are the rules. So billiard ball rules is a Margolus neighborhood. And we figure out, should we turn or not? And this makes little balls bouncing off of each other. Critters, waivers, these Tron. Anyway, these, and you see regular things like brain and life, bonks. But anyway, I had rewritten it in JavaScript eventually, C and C++, then JavaScript. And it's a huge file. And it's a little out of control, and the user interface is arcane. But here's kind of the theory of it and where it's headed. And here it is running. Let's see. Okay, what you see here, these are the cells, and we can paint in them if we like. And this is running, not technically a cellular automata, but it's more of it's a heat diffusion, and it's 8 bits per cell. So it's discrete. This is a histogram of all of how many cells are of each pixel, and a color map. And this particular color map has some nice saturated colors at each end, and then it kind of fades, and then it has a nice high contrast. You'll see why that's important later. So this rule is called wavy. I can get this. This is the user interface here. I'm running a rule called twistier marble. There's lots of rules. So I mean, there's life. Everybody's heard of life, but life is so overrated. Let's see, Brian Silverman's Brian's brain is much more exciting. It's kind of all these gliders. Rudy Rucker came up with a nifty idea of combining Brian's brain together with life, and one called anneal. Let me just show you pure anneal. Do we have an anneal here? Well, you'll see it. Anyway, if you go to the commands, you can randomize. Anneal is this big cow spotty thing. Basically, it takes random stuff and it counts how many neighbors are on, and it votes with a majority, unless it's almost a tie, in which case it votes against the majority. So that kind of smooths down all the edges, keeps white things white, black things black. So, but then on the black places, we run Brian's brain, and on the white places, we run life. So it's like 3 different cellular automata sharing the same space. One deciding which space the other 2 share. And the cool thing, actually, this is not life, this is anti-life or death, because it's the one's complement of life. And that is so that, like, empty space, like right along the shore, you see your neighbor. So to life, empty space of brain looks like stimulus. And to brain, empty space of life looks like stimulus. So the shores are stimulating to each rule. So that's breeding more, gliders and things like that. So, but anyway, if you just randomize like that. So this is a neat one because, it's composing several rules together and layering, and we can do a lot of interesting stuff with layering. And then the heat diffusions come in for that. So like if we did echo echo simply echoes the last state. Well, this isn't too visual, but echo heat puts a heat diffusion in the leftover bits. And so kind of like well, let me show you some heat diffusions that are pure. But basically, this is like a layer of heat diffusion on top. And the little critters happen to be kind of causing heat and polluting things. So we can do some weird things with the mouse wheel. But let's do a normal... anyway, before I go to heat things, I wanted to do the worms. Okay, this is a Zhabotinsky reaction. So these are great. Slime mold does this, or all these chemical reactions tend to do this kind of thing. So they're making... there's an attractor where there's a pattern that starts spiraling out, and there's a feedback loop here, so we can make this less horrible looking by doing this. One has a 5-step phase. So now what happens is we get these certain ones in patterns that start spiraling and sending waves out, now there's a related one. Let's see, rule. These are yuppie worms. See how they're all like uptight and angular? Hipster worms are a little mellower there. They've got some kind of curvy things, but then bohemian worms are the really cool, rough, relaxed ones. So I particularly prefer playing with the bohemian worms. But anyway, this is a Zhabotinsky reaction. A lot of these things simulates things that happen in the real world, like physics and chemistry. And then this one, this is John von Neumann's 29-state cellular automata, which can reproduce itself, but you have to give it exactly the right input state. So anyway, let's go on to this heat diffusions. I was trying to get the marble effect that you get inside of a book cover with the paint, wiggly paint. And let's see. So I wanted to diffuse heat. See, if you have a simple one, let's see. A lot of these just, like if you average your 8 neighbors, the heat will spread out. But this kind of dithers. So there's like a leftover after you average. And what it does is instead of throwing that leftover heat away, it carries it over to the next cell. So you get this. Now, if I make a really big brush and paint out, ooh, okay. So see how we get these nice air diffusion dither-like patterns. Now, the whole system can be heated up like this, That's heat, woo, heating up, see, adding a number. Watching the histogram. See, he's going over to the right. Boom. And the whole system could be cooled down over time. And then when you hit 0 or 255 at the end, you wrap. So this is going to get a little weird, but smooth it down here. So now I can paint in this with like the value of 0, right? And you see when it gets mostly the same color, you start to get these nice little artifacts, kind of quantum tunneling or action at a distance. You know, they kind of interact with each other even though they're not next to each other because the leftover is tunneling through multiple spaces per frame. So this is where it's not really like a cellular automata, because you can't really get cellular automatas to have action at a distance, but that's kind of what's going on here. Anyway, to make this more concrete, I will use the painting tools. So circular brush of a size small and a high value. This is a heat simulation, so I'm going to put a high value. Now it's getting concentric rings. So if then I went to a low value and painted in the middle. Oops, that was the size. Okay, low cell. So now this is sort of shaped like a volcano if you think of it as a height map. So they will smooth out eventually to all the same. See how the histogram is showing they're all trending towards the average, and then you'll get a nice smooth area. But if you paint in it, you've introduced these hills in the height map or gradients in the heat map, if you think of it that way. So the other thing is the mouse wheel just adds heat or subtract heat from the whole system. So when I move the mouse wheel up, the whole system rises in temperature. And whoa, here. I put a little niche in the color map here. So we can kind of X-ray one little slice. And let's see. So this lets us kind of X-ray a rule. So like wavy marble is different than fiery marble. See, fiery marble goes up, of course, because it's fire. But if we were to put a little, you know, okay, whoop, ooh, oh, it went out. So this is fiery marble. And then you can frolic around in there. Or even, let's see. Oh, wait, see, the cool thing is when this, see, this is the histogram, the heat of the system lowering down, lower and lower. And that is the frob that controls that. So frob target. Okay, now it's going towards 0. Now watch what happens when it hits 0. Boom. Okay, you get chaos. You get kind of random blobs because the coolest part of the system, I'll slow it down here. The coolest part of the system suddenly has a really hot point in it that then diffuses out. So it's kind of like, you know, raindrops or something. But, you know, this adds all this nice chaos to the system. So when it gets down to 0. So, and you can do that with the mouse wheel. So right now it's not near 0, but when I bring it down and then smash it against 0, we'll get these blobs, right? But now it's high again. So that's kind of putting more heat into the system instead of crashing. So, and then you can take it to the other end of the spectrum. Boom. See how it hits? So first it hit, it's all synchronized now, and then it hits, and then you have like, so it's kind of hard to explain, but if you've played with it for hours, it becomes kind of interesting. So, but basically it's a heat diffusion, but with this weird mathematical twist at the edges, which has no parallel in physics or reality, but looks cool. So, but what you can do, I really like getting it, I like getting it smooth and with a high contrast, because these, let's see, anyway, there's other ones than fiery marble. Freaky marble, of course. So, freaky marble, well, the basic test is to just blast it with randomize. Boom. See how it cools things down. Because that brings you to 50% average, which is high contrast. And then like, heat it up a little bit and then try drawing in it with a little bit of contrast. So, okay, the thing about these marbles is that they're adjustable. Let me do a couple other marbles so you can see the range. Twisty marble. So once I got Freaky working, I wanted to see if I could make it twist. So, okay, that's sort of twisting. Now, the way to make it, then there was twistier marble because that's not twisting enough. So that's twisting even more. So, okay, this will be a good one to demonstrate how it twists. Oh, and fuzzy marble? See, it's fuzzy. So, and then funky flower is a little different in a different class. But twistier marble, I'll show the way you can control this. So now we're drawing in it, and it's definitely twisting. So what we have is there's 3 phases. Okay, well, there's phase offset. Okay, the way to do this is to dial all these down and show them one at a time. So there's several phases. Boop, 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 boop. Stop. Okay, there. Okay, so what we have is 16 different convolution kernels. And this is one of them. And obviously it goes down and to the right. And we can draw on it as it goes by. So now phase offset picks which one of those you get, okay? So here, I'll go over them here. So there's down. There's down and to the left. There's left. You know, so we have all these directions. And then we have an even more, I guess these are even faster in that direction. So, okay, so basically we've got these different kernels we can switch between. So when it's like that, but the thing is, right now everything's dialed down, so all that affects it is the phase offset. So this is like the DC voltage, okay? Now, on top of the phase offset, what you can do is, for phase shift step is time. So I'm going to dial time into the equation. So every, 15, it takes the time and it shifts it by 15. And so it doesn't change very often. So now every, 2 to the 15th steps, it shifts or it goes to the next offset. So, okay, so this is super slow. Okay, now this is less slow. Okay, so this one's changing fairly frequency. Now I'll go really fast. Okay, here's super fast. And then, so this is stirring it basically. So see, we have how fast do we stir it? So if I just go whoop, whoop, so see it's shifting a little there. So, oh yes, you can see it does a slow spin and then a fast spin. See that slow, fast. Okay, so this is the phase here. If I put it even lower, I'm slow. This is like Turtle Graphics where the world moves instead of you. And then this is fast. So all I'm doing is drawing a point in one place and in a wrapped world, and the changing the convolution kernel is moving the world out from under me. So let's see. So we'll do that even slower. Yeah. Okay. So see how it wraps, and then you're like, this is the Tholian web. So So, and the effects of the last one kind of faded out. So, anyway, so that's weird. But, okay, now we can say phase shift cell. It takes the cell's value into account. And this is a kind of subtle one that you need enough cell value differences. But here's a good example, because we have a crease. And the crease is because, see, there's this weird crease. And the crease comes from the fact that the cell value changed. Here, I can change it with the... Ooh, okay, see that wrinkle in time, so to speak, it's a wrinkle in phase. And the reason it changed phase was we got to a lower cell value. So maybe if I made my painting tool a little larger. So anyway, so rules. So that's the phase shift cell, and we'll turn that one off because we want to show the other ones pretty clearly too. So, but I'll leave the step on. Or wait, no, I'll turn step off. Now, then there's the spatial phase. Okay, whoa. So phase shift Y, when it's all the way, it's very high frequency. It only shifts it a little bit. Well, it shifts as none. So the Y position switches the phase. And then we make it lower frequency. So we can have it kind of blocky, or we can have it pretty fine, or we can turn it off. And then the X is similar. Like that. So now so if I draw in the X shape, I get zigzags along X. And this controls the frequency of the zigzags. And then if I want Y zigzags the same as X zigzags, then I can get some nice freakiness. But it's kind of cool to make different frequencies of zigzags. Who would have ever thought that? So let's see. So basically your X and Y phase shifts let you figure out how chunky X and Y changes will be. And then kind of get the right frequency for everything else you're doing. So if you want to do like a Lucy in the Sky with Diamonds effect. So, not that I recommend operating heavy machinery under the influence. But let's see. So yeah, you might have a lower frequency Y by 1. And then, oh, they look like people. Oh my God. So now, so this is all cool and fine, but then let's add a little cell shift to break up. See, I put that in to kind of break up these regular patterns, because if you have an irregular cell shift, kind of adding some noise to the mix. But yeah, so there, see how that kind of just mixes things up a little bit, but is spatially kind of coherent. Now, the phase offset, of course, see that? The phase offset just changes which one you get. Now, this is all fine and well, but we haven't even put any time shift into it. So that's where the time step comes in. It's nice. If you leave it slow, it kind of bakes in the effect. Let's get it a little more. And then a little shift cell might as well. So, with the faster time shifts, then you get this wavy stuff that might hurt your brain. See, and then you can just slow down time shifting a little bit. And then when you slow time shifting down, each effect gets more time to really express itself. So, maybe if you're doing this to music, it would be interesting to synchronize it with the music's time instead of the simulation's time. So let's see, I think even more. Yeah, so I kind of like with the horizontal things. Is that a very cyberpunk kind of a thing going on? And there's other, there's other tools. There's circular spray, where you can choose how many sprinkles you get and how the size is. And just spray random stuff. And then what I kind of like is the line. And you don't really want that too fat. But making sweeps through these things is great. So let's see. So anyway, there are a lot of different rules here. And each rule is totally adjustable, because basically these rules just pick between 16 different kernels, and then the others, and then each of those is similarly adjustable. So let's see. Now, there was this really weird rule. Funky Flower actually lets you, paint in the upper 4 bits with which convolution kernel you want. So the good way to demonstrate this, and I can kind of tell a story about painting a picture here. So let's just, first, the universe was complete chaos. And let's see. Then we got a circular brush, and then we made it kind of big, and we made it 0. And we said, let's paint with 0. Boop, just bit in the middle there. So all these are running a random kernel, but this one is running kernel 0, and that just is very even. And think of this as space. It just spreads out. But there's kind of energy coming in from the chaotic edges. So now, right now, there's these kind of quantum fluctuations of space bubbling, but we could go and decide to change the Frog target of the universe. So if you have a negative Frog target, things can be very chaotic. Now, as you move down to 0 and then go above 0, whoa, things can also be chaotic at the other end, but we have different colors. Now, near the middle is 0, so things are gently coming into the center of the universe, and we can just paint more. And if you'll notice, the universe wraps at the edges, like all good universes should. So we will paint out some nice wormholes to the other side of the universe, but leave a nice chaotic core in the center. So, or rather, in the anti-center. So there is only one core of chaos, but it is in all different directions because the universe wraps. So what we can do is see there are a bunch of different kernels, and let's paint. Okay, first let's explore this kernel 0. Okay, so we use the mouse wheel to cool and heat the average temperature of the universe. But when we cool it to cold, we get these chaotic bubbles. So see, I'm kind of banging it against the bottom of possible temperatures. And if I do that really hard, then it just crystallizes it. So, whoa, anyway. Now we try to achieve equilibrium here. So now coming out of the chaos is blooming this heat and energy into our universe. So if we think of this as like space, but with maybe electrons or photons tunneling through it, we can heat it up, and this rainbow gets pulled out, and we get more like these nice, more saturated colors. And at the top, think of this as blue sky with some white clouds in it. Say that's 15. If I were to go to the tool and say the tool cell is 15, now I can paint with just a cloud, and the sky is kind of trying to come in on that. So kind of push those rainbows back there, push them back. Now, see, the trend is for everything to encroach on the clouds, and the sky will eat the clouds, and then, you know, the green and the fire colors, and then back here, and then eventually you'll get this. So, but what we can do is kind of adjust the universe's target so that it heats up a little bit. And now it kind of automatically percolates back up to the sky, and now see it's bubbling against the other end. So here, you know, this is with a little bit. But anyway, so see now when I paint, it's kind of sparkling there. The sparkle comes from wrapping around. But anyway, then let's see. I think probably what we need at this point are some planets. So let's see. Let's go to the other end and pick this rule out of the nice high contrast area and make sure the tool size is large enough to draw a planet with. Okay, so this kernel, this planet is spinning. This, you know, it's flowing down and to the right, obviously. So, and we can kind of tweak it with the, we can adjust the colors and the temperature of the entire universe here and see what effect that has on the planet. See how the, this heat here is getting bled out into it, because space conducts heat, but these other areas are kind of isolated from each other. So it's kind of weird. It's its own fictional physics. So we go and choose another kernel and try that one here. And that one's going just to the right. And then give another planet, a moon over here. Oh, and look at that, it wrapped around. And then maybe one here. Oh, that's spinning a different direction. And one here would be pretty nice too. Yes, and then we can adjust, see what, so we're having these different regions, each has a different flow going on. You can see in the histogram, the different regions. And then, that one's going the opposite direction. So maybe put this one in here, of course. I touched some of the chaos. That could be interesting. And then, okay, so we've got a few of these things going on. Let's try some of these lower rules. These are a little different. They don't move in any direction at all. They just kind of hang out. But there's sort of different diffusion constants in those areas. So, like, some are affected very quickly by their neighbors, and some are not. So, let's mix this one up a bit. See how you can really mix it up, and then it kind of relaxes out again. But anyway, I haven't even used all the rules, but I will take a left turn here and change to a ridiculous instruction set cellular automata and see what happens. Whoa! This is another one where the top 4 bits say which instruction to run, and the bottom 4 bits are what it runs it on. So, for example, let's see, if I press and drag into here, I then sample that, and I can paint with life. See, this is life, obviously. Everybody knows life. So if I see another one like, oh, okay, see this one here, I want to sample and then paint with it. Whoops, what was that? Here, I'll just sample the random stuff and paint. So basically, all these different colors. Okay, so I can paint with the heat diffusion here, and that's right up next to life. So see, see it stimulates life because it's a neighbor. So let's try another random one. So there's several of these. Ooh, okay, I think this is a logic calculator. See, watch what happens when a life runs into it, or if we put it next to something. Well, see, that's too much stimulus. But if you put it here, yeah, see how the life gets sucked up into it. And let's do a few other random ones. Okay, so there's ones for moving stuff around that just copy in a certain direction. So like if we put that one down there, but then we put this one in the middle. So see how life is getting copied off in that direction. And then, that's copy in this direction. Boom. So we'll slurp the life in that direction. And then, let's see, that's up. So we'll slurp this life in the upward. So, and then let's see, I think we're getting there. Which one is that? Boom, that slurps that way. So we got a life running, and it's being stimulated by these guys, and then it's hitting the edge and getting swung out in different directions. So this is a sort of a parallel instruction set, you know. Let's see. I said it was ridiculous. It could use a better user interface, I suppose. Some of this is meant to be programmed by scripting, but, you know, don't let it stop you. Especially the von Neumann 29 state is a historical cellular automata that can reproduce itself. Oh, there we go. This is a good one. But you have to have very specific initial conditions for it to work. So, yeah, that's a nice one too, yeah. So, let's see. So you're basically painting with cellular automata rules. See, that is life, right? And then I think we have a Brian's brain. See, that's Brian's brain next to life. And then this one's shooting little things into Brian's brain, as Brian's brainifies. So see, just by being adjacent to something, they communicate. There's another life, yeah. Anyway, there's not much documentation, and there's not a lot of practical software that's been written with this, but it's interesting to play with. So, all right, I guess that's enough for now.